Good morning, everybody. Can you listen to me, please? Raise your hand. Yes, everybody. Good morning. Please raise your hand. Okay, just 2 minutes quick review. What we did yesterday. Yes, 2 minutes quick review, everybody. Yesterday we closed completely DC steady state. Okay, actually we were doing this Millman's theorem. Okay, which is called parallel generator theorem, which is applicable only to such networks which are in parallel generator form. Like all practical parallel DC generators, voltage source in series, we can convert into simple generator or single branch consisting of voltage in series with resistance. Okay, then we can simplify into single voltage and single resistance, and this is called Millman's voltage and Millman's resistance. Dual of Millman's theorem is not so practical because realizing current sources in the world is very rare. Realizing current sources are rare, so there again practical current sources in series we simplified into single current source, that is called Millman's current and dual of Millman resistance. Now this is only important, sir. This is only practical because current sources are very rare and we will just do that. Then find current I by using Millman's theorem. So because the target is to find current I in 5 ohms, the rest of the network I simplified into parallel generator form, and then we simplified into a single branch consisting of voltage source in series with resistance. But here in my Millman's equivalent, I took X positive with respect to Y, this VM polarity. You see X positive with respect to Y. But here this 10 volts, 20 volts and 40 are in same polarity, but 30 is opposite. So that is why here minus K. Okay. However, resistors are bilateral. Then yes, practical DC voltage sources we simplified into single branch. Okay. Then here Gencobit, again Millman's equivalent, we got value of VM, and then VAB. Then substitution theorem was very interesting, very interesting. We can substitute any passive element into its equivalent voltage or current. Okay, and based on that, first I asked this 4 ohms can be replaced by what? Answer is 8 volts with X positive with respect to Y. Then I gave one bit where I can represent this 1 ohm at least in 5 ways. Okay, voltage way, current way, part of voltage and resistance, part of current and resistance, and this is also voltage and resistance. So many ways. Then use substitution theorem. Yes, use substitution theorem to find the value of battery voltage E to transfer maximum power through the entire load. Now here again, battery in the load side is not allowing us to reduce. So I use substitution theorem to represent the battery as IR, and then I made it into small resistance problem. Yes, I did made it into small resistance problem. Okay, then yes, I simplified into a simple network where I got current and also battery voltage E. Now here also, if the reading of galvanometer is 0, then determine the value of source current. Okay, then source current is this 3. Okay, here also the confusion with the battery 6 volts has been replaced by substitution theorem, and I got this source current. Then here, if Vs is constant voltage source and IL is constant load current. Okay, Vs is constant voltage source and IL is constant load current. Okay, then Pmax occurs in the load if IL value is dash. IL is VL by RL. Okay, IL is VL by RL. Okay, then I got this value also. Then we came to chapter 4, basics of time variance. Okay, inductor properties we studied, capacitor properties also we studied. Okay, yes, basics, but we will expand them, sir, very neatly. Then we started inductor problems, reduction techniques, dependent source problem, unbalanced bridge. Okay, very interesting. Then we came to steady state concept. Okay, here also, though the question is just to find currents, but they are steady state currents. But remember, both are short circuits. Then how to do current division can be explained from time variance only. That is why this chapter is all about learning time variance concepts. Then law of conservation of energy, law of conservation of flux. Okay, very interesting things we learn. Okay, now we continue from there. Okay, everybody will continue from there. Okay, now I'm giving very interesting question. Okay, and I'm expecting such questions can come now. Listen to this question, everybody. Listen to this very unique and important question. Okay, and try to do it. Okay. initially switches are at position A and A dash. Initially switches are at position A and A dash respectively. Then find steady state currents, flux linkages, and energy stored in each inductor. Okay, energy stored in each inductor. Now if switches are simultaneously moved to position B and B dash respectively, and remains there forever, then determine the steady state currents, flux linkages, and energy stored in each inductor. Energy stored in each inductor. Verify law of conservation of flux and law of conservation of energy. Okay, verify law of conservation of flux and law of conservation of energy. Okay, verify law of conservation of flux and law of conservation of energy. Assume the switches are ideal. And there is no loss in energy during the transit, and there is no loss in energy during the transit. Okay, no loss in energy during the transit. And I'm giving the figure here first, then I will explain again. Three amperes, 6 amperes, 3 Henry, 6 Henry, switch S1, this is switch S2. Initial positions are A and A dash respectively. Final positions are B and B dash respectively. Now look at the circuit, sir. Everybody look at the circuit. Very carefully look at the circuit. See, that means initially switches are at position A and A dash means they become independent loops. They become independent loops. Okay. Initially switches are at position A and A dash means this becomes an independent loop and this becomes an independent loop. Okay. Then I want their steady state currents, flux linkages, and energy. Now, if switches are simultaneously moved to B and B dash respectively, B and B dash means now this becomes a single circuit isolating the sources. They become a single circuit with only inductors isolating the sources. They become a single circuit only with inductors isolating sources. Now again I need to verify the steady state currents, flux linkages, and law of conservation of energy. Okay, I need to verify again steady state currents, flux linkages, and law of conservation of energy. Sorry, steady state currents, flux linkages, and energy. And then I need to verify law of conservation of energy and law of conservation of flux before and after the change. Okay, assume the switches are ideal and there is no loss during the transit. That means as the switches are moving from A dash to B dash switch 2 and A to B switch 1, there is no loss of energy. Okay, na? Yes. Now you read this. Ideally, switches are at initially switches are at position A and A dash. Then find the steady state currents, flux linkages, and energy stored in each. Now, if the switches are simultaneously moved to position B and B dash and remains there forever, okay, and then determine the steady state currents, flux linkages, and energy stored in each. Verify law of conservation of flux and law of conservation of energy. Assume the switches are ideal and there is no loss in energy during the transit. Okay, na? So everybody, I'm giving you 2 minutes, write some answers. Then I'm going to explain this ideal double inductor problem. Very interesting. And I'm expecting such things will come. Okay. Chalo, 2 minutes, try something immediately, everybody. Yes, time up. Now see this I am going to do. See, initially switches are at position A dash. Now see sir, very interesting. So yes, I am writing first case one. Case one results are very, very interesting problem, sir. This is outstanding problem. If you can understand such ideal cases, then practical cases are easy. Case one, before change. Okay, before change. That means initially switches are at position A dash. Then what happened? This current source now switch is at A. This becomes one independent mesh, and this is another inductor. Okay, this is also another inductor, which is an independent mesh. Okay, independent mesh. Okay, independent mesh. Okay, this is now 3 amperes, 3 Henry, 6 amperes, 6 Henry. Okay, now Jello, first current through 3 Henry. Steady state current is 3 amperes now. Then flux linkage in 3 Henry. Psi is Li. L is 3, I is 3. That is 9 volt second. 9 volt second. Then energy in 3 Henry. That is half L I square. That is half into 3 into 3 square. That is 13.5 joules. Right side inductor also. Steady state current in 6 Henry, 6 amperes. Flux linkage in 6 Henry, psi is Li, 36 volt seconds. Then energy in 6 Henry, half L I square. Okay, half L I square. If you do, that is 36 into 3, 108 joules. Now here clearly, because they are independent, here both inductors are independent. Independent means separable. Independent. Okay, then I can say total flux linkage is psi 1 plus psi 2. Okay, that is clearly 9 plus 36. That is 45 volt seconds. Okay, 45 volt seconds. Equation 1. Then energy total also, yes, E1 plus E2. Okay, that is now 13.5 plus 108 joules. 108 joules. Together, it is going to be 121.5 joules. 121.5 joules. Okay, now 121.5 joules. Okay, so please understand this. Yes. Please understand this. Okay, now. So before change, yes, before change, this is how they are working. Yes, before change, this is how they are working. Okay, independent meshes, currents, flux linkages, and energies. Here also both are independent. Okay, total flux linkage, total energy. This is all before change, sir. Okay, this is all before change we got. Now what he said, now both switches are moved to position B and B dash. Okay, both switches are moved to position B and B dash. That means now sources are isolated, but inductors come in series. Now after change, case 2. Very interesting, sir. Case 2. Okay. Yes, case 2. This is after change. Now after change, both switches are coming in position B and B dash now. So both inductors become series. Both inductors become series. Three Henry, 6 Henry. Okay. Now sources are isolated. Now sources, see the meaning. The switches come to B and B dash. Now sources get isolated. Okay. Now you may say, sir, how this can work, sir, when there is no energy? That are ideal inductors, na, sir. Ideal inductors, they would have got energy from the previous state. Yes or no? Yes, ideal inductors would have got energy from the previous state. Yes, ideal inductors would have got energy from where? From the previous state. Okay, and pure inductors will never convert or dissipate. They store and retain. Yes or no? Pure inductors will never convert or dissipate. They store and retain. So in that regard, yes, in that regard, I can now guarantee that this pure inductors will never convert or dissipate, and there is no wire resistance. Ideal inductors means there is no wire resistance. So this energy, which is from the previous state magnetic stored energy, will be now circulating and making the current to flow steadily without any dissipation. That is ideal concept. So now, because they are in series, okay, because they are now in series, currents are equal. Okay, currents are equal. Okay, when currents are equal, yes, I can say now I1 equal to I2. But since psi is Li, so psi 1 by L1 is equal to psi 2 by L2. But L1 is how much? 3 Henry. L2 is how much? 6 Henry. So from that I can write, okay, psi 2 is 2 psi 1. This is equation 3. This is equation 3. Now my real step is this, sir. This is the most important step I am writing. Now, directly respecting law of conservation of flux only. Law of conservation of flux only. Now you may say, sir, why are you not taking energy? There is a very big reason which I will explain. You may say, sir, why are you not taking energy? By directly considering law of conservation of flux only. Okay, by directly considering law of conservation of flux only, that is total flux linkages before, okay, is equal to total flux linkages after. Total flux linkages before is total flux linkages after. Now, what is the total flux linkages before? See, total flux linkages before is how much? 45. Okay, na? And after is this. So solve 1 and 3. Solve 1 and 3. Okay, now solve equation 1 and 3, because total flux linkage before is 45. Phi 1 plus phi 2. But total flux linkage after is same now. So I'm equating this 3. So phi 2 is 2 phi 1. That is, if you substitute 3 in through, that is solve 1 and 3 means substituting 3 into 3 in 1. Okay, 3 in 1. See here. Here what you got, phi 2 is 2 phi 1, but here phi 1 plus phi 2 is 45. Now phi 2 is 2 phi 1. That is total 3 phi 1 is equal to 45. That implies phi 1 is 15 volt seconds. 15 volt seconds. Then what is phi 2? Phi 2 is 2 phi 1. 30 volt seconds. Okay, phi 1 is 15, phi 2 is 30, phi 2 is 2 phi 1, that is 30 volt second. Okay, phi 2 is 2 phi 1, that is 30 volt second. Okay, now that is what we got, sir. Okay, phi 1 plus phi 2 we got. Okay, and here phi 2 is 2 phi 1 we got. So total we got this, sir. Wonderful. Okay, now the students who took law of conservation of energy, I will tell why, what is a mistake. What, it's not a mistake. How to justify, I will tell you. So I took law of conservation of flux only and I got these answers. Now once I got the flux linkage, now I will find the currents again. But since currents are same, I1 equal to I2, that is psi 1 by L1 must be equal to, okay, psi 2 by L2. But because this psi 1, psi 2 we got now, this is 15 by 3 is equal to, this is how much we got, psi 2, 30 by 6, both equal to 5 amperes. So finally I conclude this I1 and I2 equal to 5 amperes. Now I am going for energy. E1 half L1 I1 square and E2 is half L2 I2 square. I2 square. Okay, na? So now in that regard, yes, now in that regard, okay, this is coming as 37.5 joules and this is coming as 75 joules. Okay, now I will find here. Now here for this case too, okay, total flux linkage is however psi 1 plus psi 2 na, psi 1 is 15, psi 2 is 30. 15 plus 30 is equal to 45 volt second. So here law of conservation of flux is satisfied. Okay, but E total will be E1 plus E2. E total will be, yes, E1 plus E2. Okay, E1 plus E2. That is 37.5 plus 75 joules. 37.5 plus 75 joules. Okay, that is 112.5 joules. Okay, that is 112.5 joules. Okay, E1 plus E2 is 112.5 joules. Okay, see now, before that total energy was how much? Total energy is 112, 121.5, and this is 121.5, but this is 112, 112.5. So here it is not, so that some 9 joules of energy is missing now. Here law of conservation of energy, law of conservation of flux is satisfied, but law of conservation of energy has to be justified, Okay, okay. Now that mathematical proof, yes, that mathematical proof, whether really law of conservation of flux is greater, law of conservation of energy greater, that mathematical proof in Laplace domain can be done. Laplace domain, I will do. Okay, Laplace domain. Now in Laplace domain, after change, now this topic we will link there in Laplace, but I'm writing directly. That means because these are the initial conditions. See, what are the initial current through inductor? See, initial current through this inductor is again, yes, 3 amperes only. This is 3 amperes only. And what is the initial current here? 6 amperes only. Now, inductor with initial current in Laplace domain, how to write? Yes, in Laplace domain, the direction in which current enters minus Li naught SL. And here also minus Li naught SL. Okay. Yes, minus Li naught and SL. Okay. So here minus plus Li naught. L is how much? 3 and 3. I naught is also 3. Okay. L is 3. I naught is 3. So overall it is 9 volt. Yeah, minus Li naught. L is 6. I naught is 6. Okay. This is minus 36 volt. Okay. The direction in which current enter is minus Li naught, and this is SL ohms. SL 3S and this is 6S. Okay, this is 3S ohms and this is 6S. Now, sir, those who are not understanding this part, leave it. I will teach you again in Laplace transform chapter, which is one of the last chapters. But now proof mathematically whether to take law of conservation of flux or law of conservation of energy is coming now mathematically. Now here, if you find this current, total current I of S, now I'm writing a KVL. Chalo, if you write a KVL, yes, minus 36 volts plus I of S into 6S minus 9 volt plus I of S into 3S equal to 0. So if you take I of S 6S plus 3S, 9S is equal to 45. So I of S is 45 by 9S. That is 5 by S. Now I of t is inverse Laplace of I of S. Okay, so I is nothing but I of t is a constant current. Okay, I of t will be Laplace inverse of 5 by S is 5 u of t. 5 u of t means it is 5 amps. That implies I1 equal to I2 equal to 5 amps in steady state. 5 amps in steady state. Okay, 5 amps in steady state. That is why we got same answers now, sir. See here, we got same answers now. See, this is also same proof now. So I1 equal to I2 is 5 amperes. Same answers we got. That is the ultimate proof we got. Okay. Yes, that is the ultimate proof we got. 5 amperes. Okay. Hence, I consider law of conservation of flux. Now, I will write the conclusion. Big conclusion. Now, the conclusion here is, yes, conclusion here is, okay. Now, this is the conclusion. Here, law of conservation of flux is verified, but okay, I will write directly. Okay, here law of conservation of flux is verified, but law of conservation of energy has to be justified. I already told now. See, I already told that point. See, this point I told here already. What I told here, see, law of conservation of flux is justified, but law satisfied, but law of conservation of flux is to be justified. Now, what is the reason? Yes, flux is considered as matter. Flux is considered as matter. Flux is considered as matter. Please understand. Flux is considered as matter. Okay. Yes, flux is considered as matter, but energy can be in any form. But energy can be in any form. Okay. Flux is considered as matter, but energy can be in any form. Okay. Flux is considered as matter, but energy can be in any form. Okay. Energy can be in many form. Okay. Na? Here some of the energy. Here some of the energy from previous state has been utilized to redistribute flux among inductors to maintain equal currents. That is wonderful concept. Okay. So flux is considered as matter, but energy can be in any form. Here some of the energy from the previous state has been utilized to redistribute the flux among inductors to maintain equal current. Okay, equal constant current. And that is a wonderful. Chalo sir, now everyone, today there is a wonderful problem we started. This is one of the extreme problem called double inductor ideal case. Okay, double inductor ideal case. See, you may say, sir, why I am coming at 7:16, 7:28? Who is this anonymous attendee? First of all, I come at 7:574. Only 32 students logged in. By 7:15, 7:20 only the number reaches 200. Actually, you people don't come. And even if I start with only 15, 20 students, again you give complaint to our schedule manager. All these days over, sir. Don't teach us when to come. This anonymous attendee, who is it? You don't teach us when to come. I logged in at 7:04. You see it, but only 17 students or 15 students were there. You people slowly come. By the time it is 7:15, 7:20, then it reaches 200. And if I start with that 15, 16 students also, initially 3-4 questions will be over, and again they keep writing. They keep on writing, schedule manager, we did not receive notes, we did not understand this problem, explain sir again to explain. All this nonsense you put. And you teach us when to come. Okay. Actually, you made us like this, not we are doing something. Okay. This anonymous attendee, if you have guts, you please talk to me. I will give you my WhatsApp number. Okay. You don't teach it. Be punctual, sir. I will also see how punctual you will be in your life. Don't worry. Okay. It's all nonsense. Some students, sir, they think that they achieved everything in the world. I always wish him such all the best. But let us see. Okay. Don't worry. Every student know that, by the time the 7:05, 7:10 also 63 students. You see the recorder. 7:10, 7:10 also 63 students it was today. I keep just observing. When it is 7:15, 7:20, 80% students join, then I start. If only 15, 20 students, okay, tomorrow you will see. 5 to 7 only I will start. You will see what happens, you see. Nonsense you talk here. Don't give such suggestions as if you achieved everything in the world. Who is this anonymous attendee? Raise your hand. Anonymous attendee, raise your hand. Who is this anonymous attendee? All of you raised on this. Nikhila and Mallareddy, you please put down your hand. Mallareddy, Vikrant Reddy, please put down your hand. Now, who is this anonymous attendee? Please raise your hand if you have guts. I will talk the truth. Let us talk the truth now. We will talk the truth. Come on. Let us talk the truth. You first of all don't give your name. You don't have the guts to give your name. You put your anonymous attendee without logging in properly. And without giving. That means you want to create nonsense here. Okay. Don't create that. I will snap you. I can easily identify who are you with your email ID and I can do nonsense. Yes, sir. Yes. Navin Sai, I know. Yes, Navin Sai, I understand. So anonymous attendee, please raise your hand. Last time. No, you don't have guts. That is a problem, sir. You don't have guts. And you teach us how to do in life as if you achieved everything more than us. Okay. Next time I will pull you out. Don't worry. I can easily call to my manager, identify your email ID and I can pull you out. Okay. Others, I'm sorry, sir. Please See, I keep observing, sir. 7-4 I logged in. 20, 17 students were there. 7, 10, 63 students. So okay, it takes time, login, computer, etc. 7:15, 7:20, 80, 90% are coming. Then I'm starting. He's not understanding that. Chalo, okay, everybody, let us leave that our nonsense, useless students. I hope they will get success in life. I pray to God such people get success, but I doubt. Okay, I doubt such students will get success in life. Okay, we will meet him one day. If we get success, we'll meet him. Okay, but he don't have the guts to even understand that. We are sorry, sir. Now you don't include everyone for your sorry. Don't include everyone. You are alone the problem who's creating problem here. Chalo, everybody, please listen now. Sir, everyone, listen now. See, this is a wonderful double capacitor problem, sir. This is a wonderful double. Actually, such double inductors, double capacitor, even capacitors also I will do double capacitors. But if you do such ideal cases, na sir, then later in transients with losses and time constant, it is easy to explain. You may all say, sir, why we are learning such ideal things which do not exist in the world? See, circuit theory is ideal. Like in machines also, ideal transformer, ideal thyristor, ideal diode. Why we learn? We assume the rules of ideal things. From that ideal rules, we deviate to practical things. That means learning practical things after learning ideal things become easy because practical things have losses. They have a lot of problems of parametric effect, frequency effect, skin effect. Okay, all these are the problems. That is why first we all learn ideal cases. What is the advantage? See, once we learn ideal things, then deviating towards practical becomes easy with comparison. Chalo, so this is an ideal problem. What he told, initially switches are at position A dash. That means they become independent loops. Okay, na? They become what? They become independent loops. Okay, then in this case, I'm now calculating the steady state currents, flux linkages, and energy, which is direct steps up. And total flux, add them, and total energy also add them. Okay, total flux, add them, and total energy also add them. So that is very easy because they are independent. Now, what happened? What happened? Now, this is a very interesting case. Now, you may say, sir, here there is no energy, but how inductors current will flow? Because they got energy from the previous state, which is magnetic stored energy, and this is pure inductors without any resistance. And because it is pure inductors without any resistance, na sir, yes, that energy will be driving the current forever. Because if they are pure inductors and that wire does not have resistance, energy cannot escape. But practically, is it possible? Never, sir. Because practically wires have resistance and that resistance keeps on dissipating energy in from magnetic form to heat form, and that becomes a source free RL circuits. So in transients we will learn it is a source free RL circuits, their exponential decay currents will come, but this is ideal inductor, na? Currents never go anywhere because that energy is not escaping anywhere and it is continuously driving the current. But I took here the most important thing is law of conservation of flux only. But the proof, na sir, I got proof in S domain. You see, mathematic proof. Now some students argue me, sir, why you took law of conservation of flux? What about law of conservation of energy? Not that I'm violating law of conservation of energy, but we have to justify that. Okay, so after taking law of conservation of flux and equating flux after and flux before same, that is equation 3 and equation 1 if you satisfy, then I'm getting these flux linkages and currents are equal. This current is 5 amperes going forever and energies we got. Okay, na? Then total flux linkage and total energy we got. Okay, total flux linkage and total energy we got. Okay, then mathematical proof in Laplace domain. That is a secret. See, the students who did not understand this mathematical proof, na sir, see this part I will teach you in that Laplace transient 7th category. Sorry, excellent chapter. It is one of the best chapters in my entire notes. But to go there, sir, it will take a lot of time. It will take so much time to go there. But once we go there, this part I will link there. So those students who are not understanding, sir, how you wrote inductor with initial condition, that I will explain. Don't worry. But now remember, this mathematical proof is the reason why I consider law of conservation of flux only. Okay, na? That proof came here. Then I wrote an important conclusion that it is not that I am violating law of conservation of energy, but I am telling that some of the energy from the previous state has been utilized. See here, energy before how much is there? See, energy before is 121.5 joules. Here energy after how much you got 112.5 joules. That means 9 joules is missing now. Here some part of the energy from the previous state has been utilized to redistribute the flux among inductors to maintain constant equal currents. That's the meaning. Okay, see if this was a practical thing, now sir, this explanation is not valid. Then source free first order RL circuit will come. current will decay exponentially. That is original, practical. Okay, but this is ideal. Such things you should learn, sir. Okay, then understanding transients become more easy. Okay, na? Chalo. Now let us go further, sir. Today we are going to the most important problem on time variance. Okay, yesterday some students were asking interesting doubts like, sir, when we should take half Li square, when we should not take. Now the doubts will be clarified today. Okay, na? So now, sir, this is the first question. Okay, on time variance. Now listen here. Plot voltage. Okay, plot voltage across. Okay, plot voltage across 2 Henry inductor. Plot voltage across 2 Henry inductor. If current through it. Okay, plot the voltage across 2 Henry inductor. If current through it is as shown below. Okay, is as shown below, and also plot power and energy functions. Power and energy functions are for the first time. Okay, power and energy functions. Okay, and verify. Okay, and power and energy functions in the inductor. Okay, in the inductor. Okay, and verify. Okay, law of conservation. Okay, conservation. Let me write neatly. Law of conservation of energy. Okay, law of conservation of energy. Okay, hence determine. Okay, hence determine a bit. Okay, hence determine a bit. Okay, power in inductor. Okay, power in inductor at t equal to 5 seconds. B, energy stored in inductor. Energy stored in inductor. Okay, energy stored in inductor. Okay, in inductor. Okay, up to t equal to 5 seconds. Okay, up to t equal to 5 seconds. Okay, and power in inductor at t equal to 5 seconds, and energy stored in inductor up to t equal to 5 seconds. Okay, power in inductor at t equal to 5 seconds, and energy stored in inductor up to t equal to 5 seconds. Okay, now first I will give the waveform. Now this is the current waveform. Current in amperes. Current in amperes versus time in seconds. This is 248 seconds, and this is 4 amperes. Okay, chalo, now again read this question, everybody. Read this statement. Plot the voltage across 2 Henry inductor. Yes, plot the voltage across 2 Henry inductor. Okay, plot the voltage across 2 Henry inductor. If current through it is as shown below. Okay, plot the voltage across 2 Henry inductor. If current through it is as shown below. Okay, this is the current shape. Okay, this is the current shape. Okay, then also plot the power and energy functions in the inductor and verify law of conservation of energy. Hence determine power in inductor at 50 second and energy stored in inductor up to 50 second. Okay, power in inductor at 50 second and energy stored to inductor. Okay, and energy stored in inductor up to 5th second. Okay, up to 5th second. Okay, now so I am doing this first problem. Later I will ask very interesting question. Okay, this first problem on time variance I will do it. Okay, this first problem on time variance I will do it. Okay, now everybody. Yes. Now see here. See here he gave current function and is asking voltage. Now this is problem on time variance. So far previous 3 chapters all DC, steady state, ideal DC, inductor was short. Never we discussed. But now in this chapter, we are really learning how inductor will work, how inductor is working. Okay, now that part we are studying now. Okay, how inductor really works. So now in this regard, first, because he gave current and we are finding voltage, now the Ohm's law for inductor is V equal to L di by dt. See, how to start is very important, sir. Because he gave current and we are asking voltage, so V is L di by dt. But suppose he gave voltage and is asking current. Suppose he is given voltage and is asking current, then we should write I is 1 by L integral V dt. Okay, see, left is the output, right side is the input. Okay, na? Excitation, response. So here excitation is current, response is voltage. So V is L di by dt I will write. Suppose I give voltage function, I ask current function, na, sir. Then you should write I is 1 by L integral V dt like that. Okay, na? Chalo. Now first, this function is a trapezoidal function. This current function is a trapezoidal. Now there is no single max equation which can define all the points. Okay, na? There is no single max equation which can define all the points. So what I will do, piecewise linearization. This is a very, very important term, sir. Piecewise linearization. What is the meaning of piecewise linearization? I will do parts by parts, like 0 to 2 to 4. See, in power electronics also how we learn, sir, like 0 to alpha, thyristor is blocking, alpha to pi, thyristor is conducting, pi to beta, inductor is releasing and thyristor is again conducting. Like that we study now, sir. So that is called piecewise linearization. Okay, this is piecewise linearization. MATLAB also will do like this only. Linearization, all MATLAB, multisim software, they do piecewise linearization. Chalo, first I will take from 0 to 2 seconds. Chalo, first if I take from 0 to 2 seconds, if I can express the current function in time and differentiate it and multiply with inductor, I will get voltage now. Chalo, first now 0 to 2. Now see, this V is, now what is the current function? This current function is like Y equal to mx. Yes or no? Yes, this current function is like Y equal to mx from 0 to 2 seconds. Okay, passing through origin. So this y-axis is nothing but current axis. Slope is how much? Opposite is 4, adjacent is 2. Opposite is 4, adjacent is 2. So it is 2t. Then this V is L di by dt. This V is L di by dt. L is how much? 200. L is how much? 200. D by dt of 2t. D by dt of 2t. So total it becomes how much? Total it becomes how much? Plus 4 volt pulse or step. Plus 4 volt pulse. I can say like step also. Okay. Yes. Step function. It is like a step. Okay. So if I correspondingly plot, no? Chalo, if I correspondingly plot voltage across inductor. Yes. If I correspondingly plot voltage across inductor. Okay. Time in second. This is voltage across inductor. Okay. 0. Now if you see 0 to 2, 2 to 4. 4 to 8. Yes. Okay. This is like 4 volt. You are getting how much? 4 volt. This is 4 volt. Okay. This is now 4 volt. Okay. Then if you go, then if you go from 2 to 4, 2 to 4, how much current is constant? Na? That is like y equal to k. Any function parallel to x-axis like y equal to k, but here y-axis is current axis. Current is constant. How much? 4. Then automatically V is L, 2 Henry, d by dt of constant. Now differentiation of constant is 0, na? 0 volts. So that is why for pure DC inductor acts like short circuit. That pure DC structure is from 2 to 4, na? That pure DC current is from 2 to 4, na? So inductor acts like short circuit. That is why now current is 0. That is why now current is 0. This is 0. Sorry, voltage is 0. This is 0. Okay, current is constant, voltage is 0. Okay, na? So now I am going from 4th to 8th second. Yes, 4th to 8th second. This function is like y equal to minus mx plus c. Y equal to minus mx plus c. Okay, current is equal to, yes, minus mx plus c. Minus mx plus c. This y-axis is current axis. Now, because here I need energy function and power function, intercept is equally important, sir. Intercept is equally important. So what I will do, I will use 2-point formula. This point is like 8, 0. This point is like 4, 4. I will use 2-point formula. Like x1, y1 is 8, 0 and x2, y2 is 4, 4. So if I use that formula here, y minus y1 is equal to m y2 minus y1 by x2 minus x1 into x minus x1. Now y-axis is what? Current axis. Y-axis is current axis. Slope is how much? Minus 1. So this is minus x. Minus x means minus t plus 8. This is the current function. Now from that, v equal to L d by dt of minus t plus 8. It is clearly how much? Yes, minus 2 volt step. It is a minus 2 volt step function. So now if you plot again, yes, from 4th to 8th second, this is coming as minus 2 volt step function. Minus 2 volt step function. This is minus 2. Okay, now minus 2. Okay, now? Okay, so please understand, sir. Okay, I will write neatly, little neatly I will write because proportionality I will maintain. Okay, this is like minus 2 volt step function. Minus 2 volt step function. So if you observe, everybody, if you observe, yes, 0 to 2 plus 4 volts, 2 to 4, 0 volts, and 4 to 8, minus 2 volts. Yes or no? See, 0 to 2 plus 4 volts, 2 to 4, 0 volts, and yes, 4 to 8 second, minus 2 volts. So that is how I demonstrated Ohm's law to find the waveform of the voltage. Now onwards you give me any function, sir. Chalo, now onwards you give me any function. Yes, now onwards you give me any function. Happily I will express voltage. Now onwards you give me any current function, I will write voltage. Or similarly, you give me any voltage function, I will write current. Okay. Okay, so that is what I got. Wonderful. Okay, that is a wonderful thing I got. Okay, now yes. Now, sir, now let us extend because what else he's asking in the question? See, after plotting the voltage, he's asking power and energy functions. He's asking. Now, yesterday one student was asking about Faraday's law and Lenz law. That concept I will teach you, sir. Very interesting. I don't know who is that student, but yesterday in the doubt session he asked, sir, how induced EMF, polarity, etc. That concept I will teach now. So this concept I will teach. Okay, concept. Now listen, sir. Okay, this is a, we got how much? This is a 2 Henry inductor. Okay, now this is a 2 Henry inductor. Okay, and current function is going from left to right. Let us say the current function. Now listen. So initially current is going from what to what? See, initially current is raising from 0 to 2 second. It is raising from 0 to 4 amperes. So no, 0 to 4 amperes. It went from 0 ampere to, yes, it went from 0 ampere to 4 ampere. Now current is raising. So here di by dt is positive now. Di by dt is positive. Okay. Then what is the voltage induced? 4 volts will be against. The voltage will induced will be 4 volts again this way. Okay. Now see the concept. That means current is going this side but rising. Current is going this side but rising. Then inductor will induce EMF to oppose that. That means this polarity of the voltage 4 volts will be such that it opposes the main. So in Lenz law minus means not negative polarity. Lenz law minus means for every action there is equal and opposite reaction. See, Lenz law minus means it is not polarity. Lenz law minus means for every action equal and opposite reaction. So here current is going this side but raising, sir. Okay. See, current is going this side but raising. When current is raising, inductor will induce EMF to oppose that. That means this polarity of the voltage should be opposite to the source voltage polarity which is driving this current. This polarity of this 4 volts should be such that it should oppose the source voltage polarity which is driving this current which is rising in the current inductor. But in my circuit theory, however, here current is entering positive terminal. See, current is entering positive terminal. Source or sink, it is sink. Yes, current is entering positive. Source or sink, it is sink. Now this is sink concept. Now in the sink concept, energy will be stored by the inductor during this period. That is how energy stores here. Actually, this energy is stored in this time only actually. Then what happened, sir? Current is constant. See, from 2 to 4 second, current is constant. Yes, 2 to 4 second, current is constant 4 amperes. Okay, current is constant 4 amperes. Okay, when current is constant 4 amperes, here di by dt is 0. Di by dt is 0. Okay, here di by dt is 0. Okay, if di by dt is 0, yes, here di by dt is 0, voltage is also 0. There is no voltage. Okay, just for formality I'm showing, but no voltage. But this energy cannot be destroyed. Now, sir, energy can neither be created nor destroyed. This energy which is stored in magnetic form, now where it is going? That is retained. That is retained. Now, in this mode, I can use the formula half Li square, which is half L is 2. What is the current? 4 square. That means 16 joules of energy it is retaining. But when this 16 joules of energy came, this 16 joules of energy came from 0 to 2 seconds only. Actually, from 0 to 2 seconds it stored, sir. Then it is retaining this energy as a memory element. This is a memory concept. Memory element. Memory element. That is how inductors are memory elements. The actual energy stored in that period of 0 to 2 when current is changing. Now it is retaining this. Then if I go from 4th second to 8th second, current is decaying of, it is negatively decreasing, negative ramp. Okay, here it is going from 4 amperes to 0 amperes. So this di by dt is negative. Di by dt here is negative. Okay, then what is the voltage? What is the voltage? Minus 2 volts. It is minus 2 volt. Yes, minus 2 volt. Okay, minus 2 volt. Now, see, now again you see the meaning of Lenz's law. Here current is going this side but decreasing in inductor. Current is going in the same direction but decreasing. Current is going in the same direction but decreasing. Inductor will induce EMF to help the source. See, when current is rising, inductor will oppose. Okay, when current is falling, it will help the source. That is the property of inductor. For every action, equal and opposite reaction. That is the concept of Lenz's law. Lenz's law polarity minus is not polarity. See, Lenz's law minus is not polarity. Lenz's law minus is to explain the concept that for every action, equal and opposite reaction. When current is rising, the inductor is opposing the supply voltage polarity. When current is falling, this voltage is helping the supply voltage polarity, which is driving this current. Okay, but in my circuit theory, that is important. So in my circuit theory, finally current is leaving positive terminal. Here in the third case, current is leaving the positive terminal. So it is a source. So this inductor releases back energy to the source. That is what is really happening. So from 0 to 2 seconds it stores, 2 to 4 seconds it retains, and from 4th to 8th second it releases back. That is the real principle of operation of inductors. Okay, now so Lenz's law is also visible here, but don't misunderstand that Lenz's law. Yes, don't misunderstand that Lenz's law is polarity. Lenz's law minus is to say for every action, equal and opposite reaction. So now power functions. Let us go to power function in inductor. Now if I go to power function, we know power in inductor is voltage function in inductor into current function in inductor in watts. Okay, voltage function in inductor into current function in inductor. Chalo, first if I go from 0 to 2 seconds, if I go to 0 to second, what is the power function now? Yes, you see here. Okay, see, voltage function is 4, voltage is 4, current function is 2t. Voltage function is 4, current function is 2t. Okay, now yes, current function is 2t and voltage function is 4. So it is 8t. It is 8t watt. Okay, now you will get here as how much? 8t watt. Okay, now 8t watt. Then if you go from 2 seconds to 4 seconds, 2 seconds to 4 seconds, yes, what is voltage function? Voltage function is 0, current function is 4. 0 into 4 is 4. So power is 0 watts. Power is 0 watts. Okay, power is 0 watts. Okay, now then when you go from 4th second to 8th second, then what is the power function? When you go from 4th second to 8th second, okay, 4th second to 8th second, let us see that now. Now here 4th second to 8th second, okay, now yes, current function is minus t plus 8, current function is minus t plus 8, but voltage function is minus 2. So minus 2 into minus t plus 8 is plus 2t minus 16, plus 2t minus 16. It is plus 2t minus 16 watts, plus 2t minus 16 watts. Okay, na? So now if I plot the current power function, so everybody I am plotting the power function in inductor. Okay, if you plot power function, okay, power in inductor in watts versus time in seconds. Okay, one is 0 to 2, okay, one is 2 to 4, okay, one is 4 to 8. Chalo, what we got? First 0 to 2, 8t watt, okay, 8t watt. That means power is instantaneous function and directly substitute. At t equal to 0, 0, at t equal to 2, 16. That means at t equal to 2, it becomes 16. So this will be a steep ramp. Okay. Okay, this will be a very steep ramp. Okay, and here at at t equal to 0, 0, but at t equal to, it becomes how much? 16 watt. Okay, it becomes 16 watt. Okay, that is the meaning. It becomes 16 watt. Okay, now. Then from 2 to 4 second power is 0 now? Yes, from 2 to 4 power is 0. Yes, from 2 to 4 power is 0. Yes, it is 0. Power is 0. Okay, now when I go from 4 to 8, when I go from 4 to 8, yes, everybody, it is 2t minus 16. Here also substitute. T equal to 4 plus or like 4.00001, just like that. It is almost 8 minus 16 is minus 8. It comes to minus 8. Yes, it comes to minus 8. Okay, and at t equal to 8, 16 minus 16, 0. It is 16 minus 16, 0. 16 minus 16, 0. Okay, 16 minus 16, 0. Okay, is like minus 8. Minus 8. Okay, so this is the power function of inductor. Okay, 0 to 2, 80 watt. Okay, 2 to 4, 0 watt, and 4 to 8 is 2t minus 16 watt. It is 2t minus 16 watt. Okay, now 2t minus 16 watt. Okay, that is the meaning. So power is instantaneous, sir. You can substitute at any time and you can argue. You can substitute any time and argue. Now see the A bit, sir. I want to argue that A bit. Now see the A bit. What is the A bit he gave everybody? Yeah, not here. Yeah, you see the A bit. Power in inductor at t equal to 5th second. Okay, power in inductor at t equal to 5th second. I can substitute now. So to substitute, because this is the expression of power from 4 to 8. Nah? So that is nothing but 2 into 5 minus 16. It is minus 6 watts. Minus 6 watts means inductor is releasing energy. Releasing energy at that instant. Negative power means it is releasing. Positive power means inductor is storing. Negative, because globally inductors and capacitors are sinks. Okay, globally inductors and capacitors are sink. But they will release energy. Yes, but when they release energy, they are said to be sinks. Yes, when they release energy, they are said to be sinks. Yes or no? That is the meaning there. That is the real meaning. Okay, now sorry, when they release energy, they are said to be source. I'm repeating, sir. See, inductors and capacitors are globally passive. But when they release energy, they are said to be active. I told such points. Okay, that is why here minus 6. Minus 6 means it is releasing energy. Okay, now that is the meaning. So now let us go to energy function. Now this is more interesting, sir. Chalo, energy function in inductor. Energy function in inductor. Okay, now energy is integral p dt. Integral p dt. Okay, integral p dt. Okay, now because it is no function here. Okay, p dt. That is integral minus infinity to t power function dt. Okay, that is minus infinity to 0. Okay, and also okay 0 to t, 0 to t, pdt. So finally, if I write this energy function in inductor will be E of 0 plus, okay, yes, E of 0. Okay, I will write neatly, sir. Let me write neatly because this is an important basic problem. Later on this, sir, everything will be understood. So I want to write neatly here. Let me do it. See, so I am going for energy function. Okay, now if you go for energy function plotting also, sir, in this we are not just calculating energy. We need to plot energy function. That's very interesting. So if you plot about energy function, yes, I can say yes, energy in inductor is integral power dt. But from what time to what? From long back to present. Long back to present. That is minus infinity to 0 power function dt. Okay, plus 0 to t power function dt. Now this is called as initial condition. Okay, this is called as initial condition. So this, if I explain, this is E of 0 plus integral 0 to t power function dt. If initial condition is there, you have to consider it. Okay, now because energy is an integration function, sir, that you have to be careful with. Sure, now let us go further. Now let us calculate these parts are very interesting. Sure, first from 0 to 2 seconds, if I go, the same formula I'm writing, this energy will be E of 0 plus integral, okay, E of 0 plus integral 0 to 2 power function. But what is the power function from 0 to 2? 8t watts, 8t watts, 8t dt, 8t dt. Okay, 8t dt. Now what is this E of 0? E of 0 is 0. Okay, E of 0 is 0. Okay, E of 0 is 0. That is understood. Okay, and this is 8t is 8 into t square by 2. That is 4t square. 8 into t square by 2, 4t square from 0 to 2. 4t square from 0 to 2. Okay, E of 0 is 0 and this become 8t integral 0 to 2 8t. 8t is nothing but 4t square. 4t square 0 to 2. Okay, now 4t square 0 to 2. Chalo, now what does it mean? See now this is interesting, sir. This is not just about substitute. We have to plot now. Now how to read this integration function? Now I'm writing a comment here. That means if how to read this integration function, energy is an integration function, remember. At t equal to 0, energy was at 0 joules. Yes or no? At t equal to 0, energy was at 0 joules. Now at t equal to 2 second, energy reaches how much? At t equal to 2, energy reaches how much? Now integrate from 0 to 2, it is 2 square, 4 fours are 16 joules. But like what function? See, this function is like ax square, na? Parabolic nature, sir. Parabolic nature. So parabolic nature. So if I plot energy function here, yes, everybody, if I plot this energy function here, everybody watch this. So if I plot this energy in joules, okay, energy in joules, okay, 0 to 2, 2 to 4, and 4 to 8, okay. If I plot this energy function, it is like 0 to 2, 2 to 4, and 4 to 8 seconds. If I plot, chalo, it starts at 0, reaches 16 joules as a parabolic. This is 16 joules now. Yes, it goes like a parabolic. Okay, that is the meaning there. That is the meaning. Okay, it is going until here. Okay. Okay, now that is the meaning. Parabolic. It's like ax square. Ax square. Okay, now ax square is going. Okay. Yes, it reaches how much? 16 joules. It will reach. Okay. Then what happened? Then what happened? Then what happened from 2 to 4? If you go from 2 to 4, okay, this energy will be. Okay. E of 0. Okay, plus integral 2 to 4 power function dt. But 2 to 4, what is the power functions are 0? That is 0 dt. So if I expand, this E of 0 now is how much, sir? Previous stored energy, na? This previous stored energy before 2 seconds. E of 0 here is previous stored energy before 2 seconds. Before 2 seconds, it reaches 16 joules, na? 16 joules. And integral 0, 0. So that means, yes, that means it retains. Yes, it retains this energy. It retains the previous stored energy. It retains previous energy. Energy at the 16 joules. At the 16 joules. It retains the previous energy at 16 joules. That is wonderful, sir. Okay, retains the previous energy at 16 joules. That is why here half Li square, here also same got same answer. See, here also you see that half Li square matched with the same 16 joules. Na? That is the meaning. That is the real meaning, sir. Okay, na? Yes. Okay, that means this energy is there at 16 joules only. It is 16 joules until 2 to 4. Okay, from 2 to 4, energy is remaining at yes, this 16 joules. Now let us go to fourth to 8th second. Now if I go to 4th to 8th second, again same formula. This EL will be again E of 0 plus 4 to 8 power function. But what is the power function? 2t minus 16. It is 2t minus 16 dt. Okay. Now here what is this E of 0? Now what is this E of 0? E of 0 is from the previous state, that is 16 plus 2t na, this is 2t. T is t by 2 again if you take t square by 2. So this is nothing but, yes, You will get this as, yes, integral of that power function you have to do. So if you do that integration, yes, if you do that integration, here t square, okay, plus this is minus 16t, But what are the limits? The limits are what? This is from 4 to 8, and this is also from 4 to 8. 4 to 8 and 4 to 8. Okay, this is also from 4 to 8 and 4 to 8. Okay, so now if you expand this, how to read this integration? This is like ax square plus bx plus c, parabolic. But how to read? Yes, at t equal to 4, initial condition. Before 4, how much it is? Energy is at 16 joules. Energy is at 16 joules. Okay, and equal to 8, how much it will reach now? Integrate, sir. Very, very interesting. See, if you integrate from 4 to 8, this becomes 16 plus t square, 8 square, 64, minus 4 square, 16, minus 16 for the 64. Now, if you remove 64, 64, 16, 16, yes, if you remove 64, 64, how much it is coming? 0 joules. Energy will reach 0 joules. Again, as what function? Parabolic function. Parabolic function. Parabolic functions are. So it will go this way. Yes, it will go this way and become 0. Okay, now that is the meaning. Yes, it will go this way and become 0. That is a wonderful meaning, sir. That is a wonderful meaning. So that is how it is going, sir. That is how it is going. Everybody should understand this. Okay, now. So yes, please understand, sir, how this is a beautiful concept. Energy is integration function. That is why the comments in the yellow part I wrote is how energy plot is done. Because where it is starting, where it is reaching, and in what function style. Where it is starting, where it is reaching, in what function style. These white colors are the functions of energy, and these green color limits are, it is where it is starting, where it is reaching, it will tell. So integration function, you have to be careful. So now once this is done, sir. So once this is done, yes, once this is done, everybody. Now what I can do? Yes, now I can plot the remaining things. Okay, one more bit he asked. Okay, once this is done, he asked one more bit. Okay, that one more bit is what he is asked. Yes, what is the B bit he asked? See the B bit, sir. See the B bit. What is the B bit he asked? Energy stored in inductor up to 5 seconds. Now energy stored in inductor up to 5 seconds. Now this energy function is integration function, sir. You cannot substitute. So now be careful. Now I will say energy stored in inductor up to 5 seconds. You have to integrate. That will be, yes, integral. I will write like previous state. Okay, I will write like previous state. That is E of 0. I will write like this. E of 0 plus integral 5. Okay, integral 4 to 5, because actual function has changed again now. 4 to 5. 4 to 5. Now power function from 4 to 5 period is what? Power function from 4 to 5 period is what? 4 to 8. 4 to 8 period power function is 2t minus 16. So this is 2t minus 16. Okay, dt. But what is the energy before 4? What is the energy before 4? Before 4 second energy is where? Before 4 second energy is 16 joules. So it is 16. Plus again this becomes how much? T square minus 16t. But you have to limit from what to what? Here we are finding from 4 to 5. 4 to 5. Don't misunderstand, sir. Energy means I will substitute. Power we substituted. Power is instantaneous function. But energy is integration. You cannot do it. You should do like this only. Originally you should do like this one. So this is now, yes, this is coming as, yes, 16. Okay. Plus t square, 25. 5 square minus 4 square, 16. Okay. Minus 16 into 5 minus 4. So this, if you see, 16 plus 25 minus 16 minus 16. So it will be 16 minus 25 minus 16, 9 joules, 9 joules. So energy stored in inductor up to 50 second is 9 joules. Okay, now energy stored in inductor up to 50 second is how much? 9 joules. Okay, now that is a wonderful problem, sir. Everyone should understand. Energy stored in inductor up to 50 second is how much? 9 joules. Okay, now. So now let us verify law of conservation of energy. Now law of conservation of energy, you can directly see this. Because energy before any excitation is 0. And energy after removing excitation is also 0. See the meaning, sir. See here function is given from how much? 0 to 8 seconds. So energy before anything is given 0. And energy after removing the signal also is coming to 0. Energy before 0 is 0 and energy also is coming to 0. That means how much energy it stored, that much energy it released. Or you can also argue here. You can also argue here. This power into time is energy now. That means area of this function represents energy stored. Area of this area here represents energy stored. Stored. Here area will represent energy released. Energy released because power into time is energy. That means area of this, yes, area of this curve represent energy. Area of this curve represent energy. Area of this curve represent energy. Okay, area of this curve represent energy. That is nothing but area is how much? Half into base into height. That is 16 joules. Here also half into base into 4, 8 minus 4, and height is again 8. That is nothing but 16 joules. Wonderful, we got. So how much energy it stored? Yes, how much energy it stored, that much energy is retained. So here also you can tell area of this power function is energy because power into time is energy. But minus I am not taking. Instead I am telling releasing. This plus is energy stored, 16 joules released. So how much it stored, that much it released now. How much it stored, that much it released. Yes or no? Here also you see. Here also you see. Energy starting at 0 and energy reaches 0. So that is also true. And energy stored up to 9 joules is also perfect problem, sir. This if you can understand, everyone, wonderful. This you can understand now, sir. This level, if you can understand, everybody, please learn this. Now, average voltage in a pure inductor is 0. Very interesting. See, average voltage in a pure inductor is 0. So, this you see, and this area of this, how much? 4 2s are 8. Here also 4 2s are 8 because this is minus 2. No? This is like minus 2. And this is like plus 4. So, average voltage in a pure inductor will always be 0. Yes, one important point. In power electronics, it is useful. Average voltage in pure inductor is 0. You see that average voltage in a pure inductor is 0. So, sir, everyone, this is one of the best problem today. And I want everyone, yes, I want everyone to read this problem thoroughly 10 times. Everything I explained. Okay, now see from the given current function, I plotted voltage function, Ohm's law explained. Then from that, I explained the concept how Lenz's law is demonstrated. But our concept of stored, retained, released is important. Released energy. Okay, released energy. Then power function, it is an instantaneous function at any point. Energy function is an integration function over a period of time. And from that, yes, energy stored up to 5. There are more things, sir. Wait, I will link one new unique thing in this problem. Don't worry. Okay, still something. So, but basic. We did all the concepts of this problem, which is basic, still basic. Okay, there are some things which we need to link. But before that, yes, gate question. I want everyone to do the gate question. Plot voltage across 5 millihenry inductor. 5 millihenry inductor. If current through it is as shown below. So everybody quick. Plot the voltage across 5 millihenry inductor if current through it is as shown below. Current, again I am taking current function only. Okay, this is like 0, 3 milliseconds, 6 milli, 9 milli, 12 milli, 15 milli. And this is now, I will take this as plus 5. Okay, this is plus 5 amperes. I will write neatly plus 5 amperes, and this I will take it as minus 3 amperes. Okay, plus 5 and minus 3. Okay. Minus 3 amperes. Okay. So plot the voltage across 5 millihenry inductor if current through it is as shown below. Plot the voltage across 5 millihenry inductor if current through it is as shown below. So I'm giving you 1 minute, right? Plot the voltage across 5 millihenry inductor if current through it is as shown below. Quick, everybody. Yes, sir. Here also, let me implement Ohm's law. I want everyone to see this. Yes. Now see here also I give current and I am asking voltage. Okay. So we know V is L di by dt because here current is given and plotting voltage again same meaning. V is L di by dt. But here two things. Now one thing, if di by dt is zero, if di by dt is zero, no change. Okay. Then voltage is zero. That means these instances. Yes. That means these instances between. Okay. Now that means these instances between. Here's something very interesting to observe. Yes, the instances between these 3 to 6, between to 6 to 9 milli are where currents are not changing, so voltage is zero. Okay, if you now plot voltage across inductor. So the instances between 0 to 3 milli, 3 milli to 6 milli, and 6 milli to 9 milli, 9 milli to 12 milli, and 12 milli to 15 milli, etc. are like zeros. Okay, so you see 0 to 3, yes, 3 to 6, yes, 6 to 9, 9 to 12, and 12 to 15. These are all zero because there is no change. Okay, na? That parts are zero. Interesting. But what about the other way? What about the other way? At the same time, if if dt tends to zero, I will never put equal to zero. Sudden change. Sudden change. See, from 0 second at 0 plus, I can say 0 plus means yes, at that zero exactly, current is shooting from 0 ampere to 5 amperes. Na? And at third millionth second, it is shooting from plus 5 to minus 3 suddenly. Na? If dt tends to 0, don't put equal to 0 because nothing will change in 0 time. That is violation of law of conservation of energy, I told. But if you suddenly change, if dt tends to 0, then what voltage will come? Then what voltage will come? V is impulse voltage. Yes, that is the difference. No change, short circuit. Inductor, if you allow sudden change in short interval of time, impulse voltage will come. Now the same formula I modify like SV is L into, okay, this is I final, okay, I final minus I initial, I final minus I initial by delta T. That is how I will write, okay, I final minus I initial by delta T. Okay, now let us calculate that, okay, I final minus I initial by delta T. So if delta T, so the meaning is if delta T tends to 0, if delta T tends to 0, sudden change, then what voltage will come? Impulse voltage will come. Okay, if delta T tends to 0, yes, if delta T tends to 0, impulse voltage will come. Okay, now let us use that. So first at the 0th millisecond, at t equal to 0th second, okay, then V is, L is how much? 5 milli. This milli is because of inductor value. So inductor value 5 milli, na? 5 milli. I final minus I initial. See, current is starting from 0 is reaching plus 5 now. Current is starting in 0 is reaching plus 5. So I final plus 5 minus I initial 0. I final plus 5 minus I initial 0 by delta T. Delta T plus delta T. Okay. Now sudden change. Yes, now sudden change will give impulse voltage. And how much is this impulse voltage? 25 millivolt impulse. 25 millivolt impulse. Okay, 25 millivolt impulse. Okay, then if I go t equal to, okay, third millisecond, t equal to third millisecond. If I go t equal to third millisecond, okay, then V equal to again 5 milli, I final minus I initial, I final minus I final is minus 3, I initial is plus 5, okay, I final is minus 3, okay, I initial minus of I initial is plus 5. Okay, because it is going from plus 5 to minus 3 now. So minus 3 is I final, I initial is plus 5. Okay, by delta T. So again, concept is what? If delta T tends to 0, not equal to 0, and V becomes how much impulse voltage, but how much is the magnitude now? 5 milli into minus 8. Okay, 5 milli into minus 8. Okay, na? So it is minus 40 millivolt impulse. So if you plot them, chalo, let me plot these two. Okay, that means here if you plot, yes, here if you plot, first is at what? 25 millivolt. Here I am getting 25 millivolt. This is 25 millivolt. Here I am getting minus 40 millivolt. Minus 40 millivolt. Then again at 6th millisecond. Now if I go at 6th millisecond, at t equal to 6th millisecond again, okay, V equal to L 5 milli. Again, I final minus I initial. See, current is going this way now. I final is plus 5. I initial is minus 3. I final is plus 5. Minus of I initial minus 3 by delta T. delta. Again, sudden change in short interval impulse voltage. But how much is the magnitude of impulse? 8 5s are 40 plus 40 millivolt impulse plus 40 millivolt impulse plus 40 millivolt impulse. Now thereafter again, sir, it continues. Okay, thereafter it continues. No, this is coming again plus 40. This is again coming plus 40. Okay, plus 40 millivolt impulse. This is plus 40 millivolt impulse. Sorry, I should write here now. At 60 milli, I should write. Okay, yeah, at 60 milli, I should write plus 40 millivolt impulse. Okay, this is plus 40 millivolt. Then you repeat, sir, again at 9th milli, 12th milli, 50. This is going to be minus 40 millivolt exactly at 9th milli. Here again going to be plus 40 millionth volt. Again here minus 40 millivolt. Only first waveform. See, only first waveform we got yeah, only up to 25 because it is starting from zero. Because the function is starting from zero, the first impulse only is actually going only 25. Okay, later it is going from plus 5 to minus 3, minus 40. Here minus 3 to plus 5, plus 40. Here like that it is going. So it is like infinite impulse state, and it goes. It later continues. Sir. If it is continuing, this also will continue. So that is the important concept here. So one way no change, inductor acts like short circuit. At the same time, sudden change in short interval of time, inductor expresses impulse voltage. But you should not argue, you should not argue that in zero time it is changing and it is infinity. That is violation of law of conservation of energy. Okay, that becomes violation of law of conservation of energy. Okay, now that you have to understand. Okay, we'll take a break of exactly half an hour. So come back by 9:15. Okay, I will come back by 9:15, sir. Pakka this time. Okay, 9:15, come back. Yes, everybody, please come back. Raise your hand. Now, see, tomorrow I may leave you by 10 o'clock. So 7 to 10 direct class I am going to take. Okay, because tomorrow I am having vaccination second dose at 11 o'clock, which is my appointment actually. See, second dose vaccination for me tomorrow 11 o'clock. So I may take only from 7 to 10 non-stop. Okay, then I will go for vaccination because that is at Miapur. I have to reach there by 11 o'clock. But sir, day after tomorrow, okay, everyone, day after tomorrow, which is on 29th Friday. Yeah, day after tomorrow, 29th Friday, okay, I am going to take from 7 to 1. Is it okay, please? Is it okay, please? Tell me yes or no. Yes, tell me yes or no here. Tell me yes or no. You write in the question answer yes or no, please. Okay. See, yes, yes. Thank you, sir. Thank you, everybody. Please cooperate, sir. Yes, yes. Thank you. Yes, thank you, sir. So, see, what I'm doing is tomorrow 7 to 10 I will take. I will leave you without break, okay? 7 to 10 without break, sir. Maybe 5 minutes break I will give just for having some cup of tea or something. But 7 to 10 non-stop I will go. I will leave you little early, okay? I will leave you little early. But day after tomorrow, I will take from 7 to 1. Okay, na? Chalo, we will complete syllabus, sir. I will do my best to complete syllabus. Okay, don't worry. As basics are building strong and strong, now teaching AC steady state, teaching transients, everything becomes more easy in future. You may actually say, sir, that is tough na. No, if you know DC perfect, AC is easy, provided you know what is phasor notation, what are RMS values, okay, what is J operator, calculations in complex mode, but everything is same, current division, voltage division, Thevenin's theorem, Norton's theorem. So because you know DC, we can easily transform to AC. Similarly, transient also, okay na? So everybody, please understand the schedule tomorrow. See, tomorrow I will teach non-stop from 7 to 10. I am having vaccine second dose at 11 o'clock, which is appointment given by the government agency. So then, because I'm a COVID patient, sir, I have to take there only, sir. That is a problem. I was previously COVID patient, so I have to take there. Then secondly, yes, day after tomorrow, that is on Friday, I will take non-stop from 7 to 1. Yeah, we'll give break in between. Okay, na? Chalo, that is a plan. Okay. Chalo, now, sir, everybody, we are into this inductor capacitor chapter, but very interesting chapter, sir. As basics of time variance we are learning. See, in the previous column, it is so interesting that no change, short circuit, sudden change, impulse voltage, that concept. Now one student was writing, sir, is it millivolt or volt? It is millivolt only, sir. See, this time scale, no one is changing. Time scale, no one is changing. The time scale at which the current pulses are changing is the frequency of the pulses. That no one will change. But the milli is coming because of inductor value. The milli is coming because of inductor value. Suppose I give the time scale for current in milli and I'm asking voltage in seconds, then rate of change has increased. That is not the way we see, na, sir. We are not traveling in time, na, sir. The signal is traveling in time with milliseconds and the frequency of pulses will also be in milliseconds. So don't bring that milli and confuse. Don't bring that milli into time and confuse. Okay. So that frequency of pulses will be decided by the time scale there, which is in milliseconds. But this millivolts is coming because of inductor value. Okay, na? So now I am giving a very interesting question. I want everyone to again attempt this. Yes. The question is, yes, if voltage current plot, okay, if voltage current plot in a passive element is shown below, okay, is shown below, okay. If voltage current plot in a passive element is shown below, then component is dash, then component is dash. This is voltage in volts, and time in seconds, current in amperes and time in seconds. Okay, this is 2 volt, 2 second. And this is 2 amp. Okay, if the voltage current plot in a passive element is shown below, okay, if the voltage current plot in a passive element is shown below, then the component is dash. Okay, I'm giving some options here. I'm giving some options. Options are like, yeah, inductor 1 Henry, capacitor 1 Farad, inductor half Henry, okay, capacitor, okay, yeah, inductor 2 Henry, and D bit is capacitor half Farad. So do this immediately. Okay, here let us see. Yes, everybody. If voltage current plot in a passive element is shown below, then the component is dash. Okay. If voltage current plot in a passive element is shown below, then component is dash. So in that regard, everybody, in that regard, now let us observe Ohm's law. See, you know Ohm's law for, yes, Ohm's law for in resistor is what we equal to IR. If this would have been resistor is a homogeneous proportional component. That means ramp current will give ramp voltage and constant current will give constant voltage. So this cannot be resistor. So resistor is ruled out. If it is a capacitor, V is 1 by C integral IDT. Yes, if it is a capacitor, V is 1 by C integral IDT. Okay. So for ramp current, integral ramp parabolic voltage would have come. For ramp current, parabolic voltage. Okay. That is also not correct. But in inductor, V is LdI by dt. Okay, that means here ramp current will give constant voltage because differentiation of straight line function is a step function. Differentiation of differentiation of a ramp is step. So yes, when it is ramp from 0 to 2 second step came, and when current is constant, it is 0 because yes, differentiation of constant is 0. So pakka this is inductor. Pakka this is inductor. So one thing is for sure, it is inductor. So in the given option, this capacitor cannot be the correct answer. Okay, in the given option, capacitor cannot be the correct option. Then here you see now, here you see, if you write the same formula, this V is L into di by dt. But di by dt means what? I2 minus I1 by T2 minus T1. That is change in voltage by, sorry, change in current by change in time. Now inductance value we don't know, but we know what is voltage induced, 2 volts. See, voltage induced is how much, sir? 2 volts. I will write at the bottom. So voltage given is 2 volts, because it is given in the graph. Inductance we know, but change in current. I2 minus I1, it is reaching 2 amperes. Okay, it is starting from 0. Then time also. It is going to 2 seconds, but starting from 0. It is going to 2 seconds from starting from 0. So if you observe, if you observe, so clearly inductance is how much? 2 Henry. Inductance is 2 Henry. Inductance is 2. So it is finally inductance of 2 Henry. Okay, na? That is a simple Ohm's law concept. Okay. So another gate bit. This is another gate bit. Yes, observe carefully. If IL of 0, yeah, I'm correcting it. If Vs of t, if Vs of t is 40 t volts, okay, if Vs of t is 40 t volts and IL of 0 is 5 amperes, IL of 0 is 5 amperes, then find, okay, then find current I, okay, then find current I at t equal to 2 second, okay. If Vs of t is 40 t, okay, if Vs of t is 40 t, okay, and IL of 0 is 5 amperes, okay, IL of 0 is 5 amperes, okay, IL of 0 is 5 amperes, then find current at t equal to 2, okay. Now this is Vs of t, Vs of t, okay, and this is how much? Yes, this is 10 ohms I'm giving, and this is 5 Henry, okay. Then this is current is asking at t equal to 2, and this is given as IL. This is given as IL. So see, these questions are, if Vs of t is 40 t, okay, if Vs of t is 40 t and IL of 0 is 5 amperes, okay, IL of 0 is 5 amperes, okay, then find current at t equal to 2. Then find current at t equal to 2, okay. If Vs of t is 40 t and IL of 0 is 5 amperes, okay, then find current at t equal to 2, okay, find current at t equal to 2, okay, find current at t equal to 2, okay na. Chalo, I'm giving only 1 minute, please. Okay, chalo, you tried. Very good, sir. Keep trying, sir. I may give you 1 minute, sometimes more time. But intention is you try, sir. In my class also, you don't know, most of you, I don't know whether you know me offline or online. See, in my real class offline also, sir, I give some 2 minutes, 1 minute for student to think. And that thinking process is ultimate, sir. That is how you can become intelligent. See, training your mind, thinking your mind requires, sir. Gate competitive exams are different. Not that you by heart something you'll get. See, if you know that you by heart something and you get gate rank or IS rank, then no one would join coaching center, na sir. Think that 1 minute think, do, try, wrong or right, your ideas are important. Okay, sometimes you do wrong, then you will correct it, then you will improvise. Sometimes you do correct, you will get confidence. So that is how, sir. See, now listen, everybody. This is a ramp voltage. Everyone watch. This is a ramp voltage across parallel RL circuit. Okay, this time voltage is given and he's asking current. Now, sir, he's asking but total current. See, He said ramp voltage is given and initial current through inductor is also given. IL of 0 means what? That means inductor already has some current from the previous state. And now you are giving this 40T ramp voltage. And now he's asking find the total current I. This I is the total current from the source at t equal to 2 seconds. So here plotting is not necessary, sir, because he's asking the value. No need to plot. Suppose if I ask plot current. Suppose if I ask plot current at t equal to, then that is a different problem. But here I'm not asking the plot, na, sir. So now in that regard, everyone, I will apply KCL. This current, yes, I will apply KCL, that this current is IR and this current is IL. So according to Kirchhoff current law, this I is IR plus IL. Actually, these are functions in time. This is not like DC, na? DC circuit analysis is over. Now we are learning time variance. So these are actually functions in time. That is I of t function is IR of t function plus IL of t function. Now common sense. Common sense. First, what is the common sense? If I give ramp voltage to resistor, current in resistor is also ramp. Current in resistance is also ramp. Yes or no? Because resistor is a homogeneous proportional component. So if I give ramp voltage to resistor, current is also ramp. And then for inductor, if I give ramp voltage to inductor, current is parabolic. Okay, current is parabolic. But initial condition is also there. So that is different now. Chalo. Now, if I expand the same formula, this I of t is equal to, okay, I'm writing here. Yes, if I expand the formula, yes, that is I of t is equal to IR of t, okay, plus IL. But IL, okay, what is the Ohm's law for current? For current, what is the Ohm's law for resistor? V by R, that is Vs of t by R. Okay, and for inductor, it is 1 by L integral V dt minus infinity to t V dt or Vs dt. Here voltage across inductor is supply only, na. Now if you expand this, this will be nothing but Vs of t by R plus this is I of 0, plus 1 by L integral, okay, 0 to t Vs of t dt, okay, Vs of t dt. Okay, so Vs by R plus I of 0 plus 1 by L integral 0 to t Vs of t dt. Okay, now if you expand this, yes, this I of t is Vs by R, okay, that is 40 t by R, plus initial condition 5 plus 1 by L, 1 by 5 integral 0 to t source function 40 t dt. Okay, now this I of t is, okay, that is 4t plus, okay, 5, okay, plus this becomes how much? This is now going to be what, sir? This is going to be now t square by 2, okay, that is 4t square. See, that is why you see in resistor, this is resistor current, okay, in resistor, this is the resistor current. For ramp voltage, ramp current will come. But in inductor, for ramp voltage, parabolic current will come with initial condition. Now current at t equal to 2, here I am not plotting, I want the value. Current at t equal to 2 will be 4 into 2 plus 5 plus 4 into 2 square. So 16 plus 5, 21 plus 8, okay, 29 amperes. That is the meaning. Okay, it is a concept of ramp plus parabolic. Okay, that functions I am not plotting, sir, is not necessary. So answer is 29 amperes. Okay, that means we demonstrated what we did here. Yes, we demonstrated Kirchhoff current law for some time varying function. That is the difference. We demonstrated Kirchhoff current law for some time varying function. Okay, now I am giving another outstanding bit here. Okay, this is also gate 2 marks. All these basics of time variance are okay. Now see this question: a practical coil, okay, of 2 Henry inductance. Now practical coil means it will have resistance or not? 2 Henry inductance and 1 ohm resistance. Okay, a practical coil of 2 Henry inductance and 1 ohm resistance is excited by time varying, okay, current as shown below, okay, A practical coil of 2 Henry inductance and 1 ohm resistance, okay, is excited by a time varying current as shown below. Okay, is excited by time varying current as shown below. Determine, yes, determine, okay, the total energy, okay, absorbed, okay, by the coil, okay, by the coil. Okay, determine the total energy absorbed by the coil up to first 4 seconds. Up to first 4 seconds. Okay, na? Yeah. So, or until t equal to 4 seconds. Okay, the practical coil of 2 Henry inductance and 1 ohm resistance is excited by a time varying current as shown. Then determine the total energy absorbed by the coil up to first 4 seconds. Now, yesterday also this doubt one student was asking, sir, what happens if practical coil is there? Here, luckily, transient solution I am not interested. But see, now both resistance and inductance are there. So that is the meaning here. Okay, here both resistance and inductance are there. And I'm asking to calculate the total energy absorbed by the coil up to first 4 seconds. Up to first 4 seconds. Okay, yes, this is 2. This is 4th second. This is 6th second. Like that, it is going up to infinity. That is the meaning. Okay, time in seconds. And this is now 6 amperes. Look at the problem. Everybody read the problem. A practical coil of 2 Henry inductance and 1 ohm resistance is excited by a time varying current as shown. Okay, is excited by time varying current as shown. Okay, determine the total energy absorbed by the coil up to first 4 seconds. Determine the total energy absorbed by the coil up to first 4 seconds. Okay, everybody, please understand. A practical coil of 2 Henry inductance and 1 ohm resistance is excited by time varying current as shown. Chalo, sir, now listen carefully. So, what does practical coil indicate? Yeah, practical coil has some internal winding resistance, and in lumped parameter we show separately. This is 2 Henry inductance and 1 ohm resistance, and this is the current function going through the coil. This is the current function going through the coil. Okay, a practical coil of 2 Henry inductance and 1 ohm resistance is excited by a time varying current as shown. Okay, and in lumped parameter, yes, in lumped parameter we show like this. Okay, na? In lumped parameter we show like this. Okay, so now we know this is inductor. Pure inductor, what it will do? Energy will be stored. Energy will be stored in what form? Electromagnetic form. But what about pure resistor? Energy will be dissipated in the form of heat. Dissipated in the form of heat. So here total energy absorbed by the coil means a part of energy stored and a part of energy dissipated. So that is the real meaning, sir. That is the real meaning here. Here total energy absorbed by the coil means a part of energy stored and a part of energy dissipated. Both we have to consider. Okay, na? So both we have to consider. Now listen carefully. So first let us talk about energy dissipated. Energy dissipated. Who will dissipate energy? Resistor. That is integral power dt. Integral power dt. Now you may say, sir, why are you not taking I square R V square by R here? That is a difference in this chapter, na, sir. We were using in DC steady state directly I square R V square by R. But these are functions in time. At least this function from 0 to 2 is a ramp, then constant. So when there is time varying function, you cannot do directly V square by R or I square R because I is not steady, V is not steady. Then we have to use the functions. But now power in resistor can be given by three formulas, either I square R or V square by R or V into I. Yes or no? I square R, V square by R or V into I. Which is more correct here because current function is there and resistance is there. I square R function is better. That is integral I square R dt. I square R. And it is going from where to where? Up to 4. Similarly, I want energy stored. Okay, I want energy stored. Who will store energy? Inductor. Power in inductor. Here again, plotting is not necessary. So it is again integral. Power is Li di by dt into dt. Here also directly I will not use half Li square. Okay, directly I will not use first because it is a functions not changing in time. Half Li square I will use when it is in study. But here, basically, fundamentally, this is how we have to do. So integral power in resistor, integral energy, integral power in inductor. But he's asking up to 4 seconds now, so limits are 0 to 4. Okay, na? So now if you expand that means current function I want. But look at the current functions are here. Now look at the current function. See, if you look at the current function, first of all, from 0 to 2 second, yes, from 0 to 2 second, it is like y equal to mx. So current function is what? Y equal to mx. That is 3t. And from 2 to 4 second, 2 to 4 second, what is that? Current function is constant. Current function is constant at 6 amperes. Okay, current function is at 6 amperes. Yes or no? Yes, that is what happens. Okay, that is what happens. Yes. Okay, so 0 to 2 seconds. Yes, 0 to 2 seconds. 0 to 2 seconds. Yes, it is a ramp function. And 2 to 4 seconds, it is 6 amperes. So now let us integrate. Now in that regard, if I go, that is from 0 to 2, current function square, that is nothing but 3t whole square into R is 1 ohm dt plus 2 to 4, current function square, that is 6 square dt. So this will be how much then? This will be like, yes, you will get something like, if you do it is 24 joules you will get. Okay, you will get this somewhere around 24 joules. Okay, this you will get it as 36 into 2, 72 joules. So total this energy dissipated will be, that is 96 joules you will get. Okay, similarly, what about that inductor then? What about that inductor first? 0 to 2. L is how much? 2. I of t, 3t. Okay, d by dt of 3t. Okay, yes, again, yeah, dt. Okay, and then again, this will go from 2 to 4. Okay, that is L is 2, I is constant, d by dt of constant. However, this part becomes 0. Okay, now if you see everybody, now if you see again this part and this part, if you see now, sir, yes, this you see 36 joules you will get. This you will get 0 joules. You do calculations later, sir. Okay, and check it also. Then you will get this total as 36 joules. Now see, energy dissipated by the resistor we got and energy stored in inductor we got. Okay, now final conclusion is total energy absorbed is energy dissipated 96 joules plus energy stored 36 joules. So total it is 132 joules. 132 joules is the final answer. Okay, just look at it. I am going to explain again. So that is why we should understand where half Li square, where I square R, where V square by R I can use. The basics will be coming here. Okay, so practical coil of 2 M inductance, 1 ohm resistance is excited by time varying current as shown. Determine the total energy absorbed by the coil after first 4 seconds. Okay, okay, that is also see. Now I will talk something very important. Like one student was asking yesterday, very good things. Now that discussion I am writing, sir. This paragraph, what I am writing, you listen and read carefully, sir. Even after the class, I give notes, now, sir. Listen, see. Now I will say that yes, here, resistor will always convert or dissipate, okay, dissipate energy in the form of heat, in the form of heat. Okay, here resistor will always convert and dissipate energy in the form of heat, which is external to the circuit. Okay, I will write in the form of heat external to the circuit, in the form of heat external to the circuit, external to the circuit. Okay, where circuit cannot recover it back, where circuit cannot recover it back, because it is dissipating, converting. So circuit cannot recover it. Okay, so resistor is a lossy element. So R is a converting. I will write this first. Converting and lossy element. Lossy element. See, I also say converting. I also say lossy. If suppose in a heater also resistor will convert into heat na. In a heater also resistor will convert into heat. There we are able to utilize that energy na. Yes or no? So in a heater that resistance will, yes, what it will do in a heater, in a heater, yeah, that will be convertible and we are able to utilize that. Yes or no? We are able to utilize that. Yes, we are able to utilize that. That is the first thing. But in a normal wires, etc., we are unable to utilize now. There it is lossy. So it depends upon utilization. If you are utilizing that heat, I say it is converting. But if you are unable to utilize, it is a lossy element. Okay, it is a lossy element. Okay. Then what about inductor? Inductor. Yes, inductor is a state element, means memory element, state or memory element. I will use this term. Inductor is a state element or memory element, and this inductor current is its state variable. Is its state variable. That is very important. State variable. Okay, is its state variable. Okay, 1 minute, please. See, yes, everybody. Actually, a call came from schedule manager, sir. Regarding tomorrow and day after tomorrow schedule, I need to confirm because the page is not updated. So just give me 1 minute. A signal problem is there. I should update. See, whatever we tell to you, and once you accept, na sir, we should update in the database. I am calling and updating because before you leave, I should update him, na sir, 10:30, 10:40. So just give me 1 minute, sir. I am updating the tomorrow schedule that it is from 7 to 10, and day after tomorrow I will take 7 to 1. Okay, we will complete, sir. Pakka, I am telling you, I will give such a big data for you that you read my notes, you will get full marks in network theory. That promise I can give you. Later, I will share my personal PDF notes. Later, I will give my WhatsApp number. Then, whatever books you want, solutions you want, that way I can help you, sir. In online, that is the thing we can do now, sir. What best we can do, we will do. Okay, just 1 minute, sir. I am now considering this schedule manager number. Just give me 1 minute. Yes, everybody. See here, I'm sorry, sir. Sorry for this delay. What to do, sir? That schedule manager, I called him and he convinced. You're also happy, na, sir. Tomorrow, if I take only 7 to 10, and then, sir, I will go from 7 to 1. Is it okay? Is it okay? So please cooperate, sir. See, some college goers are there. For them, we will do again, sir. Don't worry. See, what schedule manager told is some college goers. See what they told us, sir. College goers, they were complaining, sir. We cannot attend full. See, for college goers separately in December, we will put again, sir. Revision. Okay, revision means I will teach again. So all the remaining college goers of EC, Triple instrumentation, all I will combine and teach them, sir. Okay, na? That we will plan. Don't worry. Because some college goers are also there. We should respect them, sir. Full-time students, we are ready anytime. But college goers, no, sir, they have classes, they have exams, semester exams are going. We will do that also, sir. We will take care. But you please contact our schedule team, etc. And accordingly you plan, sir. Please, okay? Chalo, now in that regard, everybody in that regard. Chalo, now see, sir, I want to write a very big comment here. See here, we understood that it is a practical coil with inductance and resistance. And then we got this, okay? Now here resistor will always convert and dissipate energy in the form of heat, okay, where circuit cannot recover it back, okay. It is a converting and loss element, but inductor is a state element or memory element, and inductor current is its state variable. So see, this is a very important point, that inductor current is its state variable. Inductor current is its state variable, okay, variable. As this component, as this component, yes, as this component respond, okay, only when there is any change in current, as this component will respond only when there is change in current, okay, which actually happened, yes, which actually happened, okay, which actually happened from 0 seconds to 2 seconds, okay, which actually happened from 0 seconds to 2 seconds, okay. So that is what inductor, sir, first when it operated from 0 to 2 second only. That time only it stored energy, okay. Yes, this component will respond only when there is change, which actually happened from 0 to 2 second. Yes, during this time, okay, during this time, it stored energy. Okay, during this time it stored energy, okay. Later, yes, later, okay, later it retained this stored energy, okay, as long as current is constant flowing, current is constant through it, as long as current is constant through it, as long as current is constant through it. Hence we can say, energy stored in inductor energy stored in inductor up to 4 seconds is energy up to 4th second. Yes, hence we can say energy stored in inductor up to 4 second is energy up at 4 second, which is also equal to half Li square, where current at t equal to 4th second also we can say. See, this is a very important point. Energy stored in inductor up to 4th second is energy at 4th second. Energy stored in inductor up to 4th second, because inductor is a memory element. Like if I say, what is the knowledge you gained from LKG to today is knowledge today. See, sir, we are all memory elements now. We are all memory elements. If I say, what is a knowledge you got from your 10th class to today coaching in ACE Academy, is knowledge today. In between, we forgot so many, we remember so many, but knowledge you gained from LKG to today is knowledge today. Like that. So, because inductor is an energy element, energy stored in inductor up to 4 seconds is energy at 4 seconds. There is nothing but, see, what is that half L is 2? What is the current at 4th second? See, what is the current at 4th second? Everybody, current at 4th second is how much? 6 amperes. Current at fourth second is 6 amperes, na sir. So if I substitute, this is 6 square. That is nothing but 36 joules only. See, same answer we got na. This is also 36 joules only we got na. Energy stored in inductor up to 4th second is energy at 4th second. That is a very, very important observation. That is a very, very important observation. Okay. So I will also write a note. I will also write a very important note. Okay. Similarly, okay. Similarly, okay. Yes, for capacitor. Yes, similarly for capacitor. Yeah, voltage across it. Voltage across it is its state variable. Okay. Similarly for a capacitor, voltage across it is its state variable. Okay. Similarly for a capacitor, voltage across it is its state variable. Similarly for a capacitor, voltage across it is its state variable. Okay, voltage across its state variable. Okay. Now, see, this concept I will link to the previous problem. See, sir, this I will link. This is wonderful. That was the question asked by one student to me. See, now because we understood this, I did what here in one of the previous problems. See, in one of these today's previous problem, which is time variance problem, you see here I plotted voltage from the current, then power function, then energy function. Now we calculated energy by exact method. Now if I put that idea, now that idea is, yes, energy stored in inductor up to 5 is energy at 5. Yes, I will say energy up to t equal to 5 seconds is equal to energy at t equal to 5 seconds. Energy at t equal to 5 seconds. Okay, that is nothing but half L I square. This current at t equal to 5 seconds. This current at t equal to 5 seconds. This current at t equal to 5 seconds. Okay, now this current at t equal to 5 seconds. Now, but what is the current function? See, sir, everybody listen. See, the current function we got. See, current function from T4 to 8 is how much? Minus t plus 8. This is minus t plus 8. Current function from 4 to t is minus t plus 8. So, if you substitute that, yes, if you substitute that, so this I at t equal to 5 is minus t plus 8. Minus 5 plus 8, which is how much? 3 amperes. 3 amperes. So energy is also equal to half L I square. That is 9 joules. 9 joules. Same answer. Same answer matching here. 9 joules. So energy stored in inductor up to, yes, energy stored in inductor up to 5 seconds is energy at 5 seconds. Energy at 5 seconds. That is a very important thing. Yes, this is a shortcut. This is a shortcut. Shortcut for inductor because current is its state variable. This problem, what I did here, yes, this problem, what I did here, I am linking there. Okay, now linking there. Okay, now take your time to learn, sir. Now I am asking a question. In the above previous question, okay, previous question, okay, in the above previous question, find a bit, okay. Energy dissipated by coil from t equal to 4 second to t equal to infinity. B. Energy stored by coil up to t equal to infinity. Total energy absorbed by the coil, equal to 4 second to t equal to infinity, and change in stored energy from t equal to 4 second to, okay, t equal to 4 second to t equal to infinity. So everyone quickly answer this. Please. See, the previous problem is this problem only. Yeah, this problem only. See, this problem, we got something very interesting discussion. First, we calculated normally. Then this paragraph was very important because inductor is a state variable, inductor current is state variable. From that, I got this direct answer also. And for capacitor also, voltage across it is state variable. Now, from that, I am asking in the above problem, find energy dissipated by the coil from fourth second to infinity. Be it energy stored in the coil up to infinity, total energy absorbed from fourth to infinity, and change in stored energy from fourth to infinity. Okay, change in stored energy from fourth to infinity. Shall I do it now fast? Okay, in the above previous question, find energy dissipated in the coil from fourth second to infinity, energy stored by the coil up to infinity, total energy absorbed by the coil from fourth second to infinity, and change in stored energy from fourth second to infinity. So now see A bit. Who will dissipate? Resistor. So from what time to what time? Fourth second to infinity, I square. But from fourth to infinity also current is constant. Sir, current is constant. So if I put that, yes, I square, that is 6 square into R1 dt. But as upper limit is infinity, it is infinity joules, infinity joules, infinity joules. Second bit, energy stored up to infinity. See, energy stored up to infinity is energy at t equal to infinity. But current at t equal to infinity is also 6 only. Now that is half L I square. That is also 36 joules. That is also 36 joules. C bit. C bit. What is the C bit, sir? Total energy absorbed. Total energy absorbed. Now here E absorbed is energy stored plus energy dissipated. Energy dissipated. So energy stored is always 36 plus it is infinity. So 36 plus infinity is also infinity. But B bit, change in stored energy, change in stored energy, change in stored energy is 0. Why? Because actually energy stored from 0 to 2 only. Actually energy stored from 0 to 2. Later it is just retaining. So there is no change. Change in stored energy is 0. Read this are very interesting bits. Read this please. Okay. Yes, read this bit. Very, very interesting. Okay, na? So with this complete introduction to inductors is over. Now let us start capacitors. Yes, capacitor concepts. Okay, na? Yes, first IES objective. This is C, 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 and C. I need C total. And I'm asking general question. It is a ladder network. It is a ladder network. And this is now 3 microfarad, 6 microfarad. This is 2 microfarad. Again 4 microfarad. This is 4 microfarad. 4 microfarad. And this is 3 microfarad. And I want this C total. Chalo, everybody, quick, 1 minute. 1 minute. We started now capacitors also. Everybody, 1 minute, do it fast. Okay, everybody, chalo, simple bits na sir, no time to waste. See, this is not a bridge. First bit is not a bridge because there is no element here. It is a simple node. Don't confuse. There is no element here, so it is not a bridge. In fact, these two are parallel. But capacitors in parallel, add them 2C. And these two are also parallel, add them 2C. Now 2C, 2C series is C farads, C farads. Now this is a ladder network. Okay, it is a terminated ladder. It is not infinite ladder, please. Here I am not giving infinity. It is a terminated ladder. Then how to reduce now? See, 3 and 6 series. Yes, 3 and 6 series. How much? 2. 2, 2 parallel 4. 4, 4 series 2. Okay. Yeah. Then let me correct it. See, this 3 and 6 series is now 18 by 9 2. Okay, ulta formula. 2 to parallel 4. 4 4 series 2. Now 2 in parallel to 4 6. Now finally 6 is in series to 3. 2 microfarad is C total. Okay. So series parallel formula you be careful with. So now I'm giving another 2 bits. Now this is a IES objective. IES objective. What is C total? Okay, this is an IES objective. What is C total? C total. C, 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 C farads, C farads, and C farads. Okay, and this is a gate bit. Wonderful gate bit. What is CXY? What is CXY? This is X and this is Y, and this is 0 volts. CC, CC, CC. This is CS, this is CS. Chalo, I need CXY. Quick, sir, everybody, 1 minute now, 1 minute, quick. Okay, everybody, chalo, I'm doing now. Listen, see between this node, see you want C totals are, but between this node and this single node, yes, between this node and this single node, yes, all three capacitors are parallel. C, C, C parallel. Yes or no? C, yes, C, C, C parallel, that becomes 3C. Okay, na? It's C, C, C parallel become 3C. Okay, na? Yes, these are all parallel because capacitor series parallel formula is ulta, na, sir? Yes, C, C, C parallel become 3C. Okay, this is 3C. And right side also between this node and this single node, between this node and this single node, again CCC parallel, this also become 3C, this also become 3C, this also become 3C, this also become 3C. So this is one terminal and this is one terminal, this is one terminal and this is one terminal. This is one terminal and this is one terminal. Now these three become series. These three become series. Let us say C dash. 1 by C dash is 1 by 3C plus 1 by C plus 1 by 3C. If I take LCM 3C, it is 5 by 3C. So C dash is 3C by 5. So C dash is 3C by 5. Now final answer. Now I am writing final answer. Finally, the C total will be C plus C dash. That is nothing but C plus 3C by 5. Answer is 8C by 5 farads is the answer. Okay, na? 8C by 5 farads is the answer. Okay, na? It is 8C by 5. Okay, na? That is the correct answer. Okay. So now you look at the next questions are very interesting. I want CXY. See, I want the capacitance between X and Y. But see here, there is one node which is at 0 voltage and there is one node which is grounded. That is also 0 volts. There is one node at 0 volts. There is one node at 0 volts. Okay. Now this is not a balanced bridge concept, please. Don't say, sir, bridge is balanced. This is CS and CS. This is CC and CC. That also not possible. So, but there is one node at 0 volt, but there is one node at grounded. That is also 0 volt. If you can identify such nodes which are at same potential, you can virtually join them. You can virtually join them. So now if you virtually join them, now this CS, yes, this CS between this node and this node is nothing but this node and this node now. So I will shift that CS here. So the same CC I will write here. Okay, already this CC is there. Okay, but this CS I'm shifting like this. Okay, yes or no? Because between this node and this node CS, I will write between this node and this node CS. Now right side also you see this is CS. This is CS. But again between this node and this node CC, this also if you shift, this also becomes CC. This also becomes CC. And this is grounded. And you are looking between X and Y. And you are looking between X and Y. Now if you observe, these two are parallel and these two are parallel. Now this ground is a floating terminal now. See, when you are analyzing between X and Y, now in this case, when you are analyzing between X and Y, now in this case, this ground is a floating terminal. This will not affect the circuit capacitance. Okay, if I ask capacitance to ground, then that is a different question. But here, you are asking between X and Y, this ground is a floating terminal. So first logic is, if you can identify such nodes which are at same potential, you can virtually join them. If you can identify such nodes which are at same potential, you can virtually join them. So this is CS and this is CC. Now these two are parallel now. So now what happens? Yes, this CC plus CS is in series to CC plus CS. Becomes CC plus CS by 2. CC plus CS by 2. Okay. And here already this is X and Y. Okay. X and Y. Okay. X and Y. This is going to be like this. This is CC. Okay. CC plus CS is in series to CC plus CS. That is CC plus CS by 2. So CXY will be, if you take all in parallel, CC plus CS plus CC by 2. Okay, I will write neatly. Yes, CC plus CS by 2. So the overall answer is 3CC plus CS by 2. 3CC plus CS by 2 farads. 3CC plus CS by 2 farads. 3CC plus CS by 2 farads. Okay, that is the answer. Chalo, we'll take up doubts today. Tomorrow, remember again. See, tomorrow 7 to 10 non-stop. Day after tomorrow 7 to 1. Okay, na? So tomorrow 7 to 10 and day after tomorrow. See, college goers, others, na sir. Please don't worry. I will plan for something else and we will take up in December, sir. Okay, in December, I will just go. Okay, we'll plan accordingly. No injustice to any student. That I will take care. But meanwhile, attend other subjects and take care. And my subject, na sir, directly like this, learn with lot of problems. You will get everything. Okay. Chalo, now doubts, please. First, Bemelindu Swine, please tell me.
Yes, sir. In the yesterday problem.
Tell me.
Sir, yes, you said that flux linkage will be for parallel path. Flux linkage will be same. Then again, I think that if at the steady state, this will be short circuit. Then voltage also.
Voltage is zero. That is why voltage is zero, but flux linkage is there. But when this flux linkage came, because of now we are understanding this topics today that energy stored during that change, energy would have stored, and fluxes would have established in the magnetic form. And now, as current is flowing in steady, that energy is retained.
Okay.
That energy retained will make the flux to retain there, like an electromagnet. See, in electromagnets also DC, battery you suddenly give, during transient state, that inductor will store energy. And once it is in steady state, inductor is short circuit actually. But as long as the current is flowing, it is maintaining and retaining that energy which stored during the transient state.
Okay.
Understood, na? That is why this ramp problem today I took. And then next when I go to transients, solutions also we will do that 0 plus problem, 0 minus problem. Then you should understand that 0 plus what happens impulse. That is how they store actually.
Okay.
Right. Vishnu Ajit.
Sir, my doubt is in that 4 bits of problem you explained right before.
Tell me, Vishnu. Tell me. I understood. Now tell me what is your doubt there.
Sir, my doubt is in that. Could you take that, sir?
I'm going there. This problem. Tell me.
Here, sir, this energy dissipated, if you calculate this, next slide,
Ah,
the energy dissipated comes out to be infinite joules. Sir, but the instant during the transient, that is during that slope from 0 to 2 seconds, the energy stored itself is finite number.
energy stored is finite number, correct?
Then how is that energy dissipated becomes infinite, sir?
Because to maintain the stored energy up to infinity, current is also going up to infinity. Na? In inductor, always remember to maintain energy up to infinity. That means you see the waveform, it is an unbounded signal. This is an unbounded signal.
Oh, okay, sir.
That is the meaning. If like the previous case, if I give the first problem, what I did is a bounded signal. That means here in this problem, if I would have calculated here, energy dissipated also would be finite.
Okay, sir.
Okay?
Yes, sir. So energy is infinite means power is 0, no, sir?
No. Energy, not that way. See, power is rate of change of energy that could be at an instant when these changing functions are coming. Like even in this also, that is why I cover such problems. See, in this case, what happened? See, when there is change, the power function came.
Yes, sir.
Power will tell only when there is rate of change of energy, but that does not mean that if energy is constant, power is 0. But power instantly when the change occurred happened actually. Okay.
Yes, sir. And sir, one last thing, sir. So inductor in generally will only store that energy when it is in the transient state.
When there is change in state, it will store or release. But once you maintain constant, it will retain memory element.
So for example, for a time bounded like the trapezoidal you explained, during the 0 to 2 seconds, since there is a change in current, it will store that energy.
Yes.
And between the interval of 2 to 4, since the current is constant, there is no change, it will retain that energy. And again, from 4 to 6, since there is a reduction in current, this energy will contribute to increase that current.
Yes, release. It releases back.
Okay, sir.
Okay.
Yes, sir.
Right. Then Akshay.
Hello, sir. That we did a problem with the square wave kind of input, right?
Yeah, tell me. I understood. What is your doubt?
Sir, there we calculated voltage using V is equal to L into delta I by delta T. Sir, but like when we substituted, it was kind of like delta T was 1, no, sir, like in the calculations.
In the calculation, what is your doubt? We substituted?
Like we substitute the value of I, L, and then I final minus I initial values we substituted, but delta T in that, like when we did that, it was actually looking like it was 1, no, sir. Like in the next slide.
It is not like 1. It is not like a 1. See, delta T, what is the meaning? Sudden change. See, the argument will be sudden change, but not in 0 time. Sudden change in current is like impulse voltage. But never I will take like 1. Ideal impulse concepts we are learning here actually, but practically, let me tell you, now clarity I will give you. It's the same problem when I go to transient. Sir, just listen, don't write. See, if I go the same problem in transient with practical RL and time constant, sir, see the current shape will actually be like this, like this, like this. This is practical impulses. You see in pulse and digital circuits, other subjects, these shapes only.
Yes, sir.
Here ideal inductor, that is what ideal impulse we have to teach means in 0 time only, na?
Okay, sir.
But never put 0. If you put 0, then V becomes infinity is violation of law of conservation of energy.
Yes,
Tends to 0, limits concept.
Okay, sir.
Okay?
Okay, sir.
That is how ideal things can be explained to understand physical world. But putting 0 is violation of law of conservation of energy. And then later in practical things, when we come the same level of problem, as we go deep and grow into the subject, their transients, impulse, ideal impulse never exists. We only study. They will be like this exponential decay impulses.
Okay, sir. Okay, sir. Sir,
Okay.
also, yes, sir. Sir, one more thing, like today's last problem, capacitor, equivalent capacitor.
Tell me.
Sir, there that the polarity would be like different, no? So like for CC, the positive terminal would be at top, and for CS, the negative terminal would be at top.
See, this is positive. Suppose this is positive and this is negative. The same positive will come here and negative will come here.
Okay, sir. Like you usually for capacitor, like now we take it as negative, no, sir, the notation.
If you swap this along this, this positive and positive are matching, and negative will match. Here also positive and positive will match, negative and negative will match.
Yes, sir. So like there are like two types of capacitors, no? Like capacitors having polarity and capacitors which are like doesn't matter regardless.
That is nothing to do with this application. Suppose if it is a polarized capacitor, in your electrolytic capacitors, there we have this plus and minus. In polyester capacitor, you can give for AC. This is called unpolarized for AC. Unpolarized capacitor for AC, polarized capacitor for DC signal. Here you can define. See, suppose in this problem, if you define what type of input, I will take accordingly. Suppose you say, sir, this is an AC problem, then I will take unpolarized capacitors. But if it is a DC problem, then I will take all DC polarized capacitors and do the problem. That is the meaning.
Okay, sir. Okay, sir.
Okay, now?
Okay, sir. Thank you.
Right,
Sir.
right.
Okay.
Pratyush.
Hello, sir.
Tell me, Pratyush.
Sir, in today's first problem, we have calculated the energy before change and after change, no, sir.
We have calculated energy.
Before change and after change of switches, no, sir.
Tell me. Double inductor. Tell me.
Sir, we have energy loss, sir. You have said that energy is lost due to redistribution of flux, sir.
I won't say energy is lost. My argument is because to satisfy, there is no other way to argue. What I told, I never say it is lost. That energy has been utilized to redistribute the flux. I will never say it is lost. Maybe some energy is taken in a form which we don't know, where it is redistributing the fluxes such that the current is constant and equal.
Sir, what is the meaning of that redistribution of flux to get the constant current, sir?
Because previously, where is the flux? Previously, what are the flux linkages? See, flux linkages is 9 volt and 36 volts. But after change, where the flux linkages came? After the change, the flux linkages came to, yes, this 15 volt second and 30 volt second.
Yes, sir.
So, who is doing that? That energy is helping there.
Okay, sir. That energy is utilizing to convert the first 5-1 to 15 and 5-2 to 30, sir. Okay, sir.
That is the meaning there. Because if it was a practical thing, sir, I would have explained that energy would have got in register or in a switch. That justification would have come. But here, all ideal things we are teaching, sir. That is the way we have to conclude. But if it is a switch, is there some losses will be there in the switch contact wire? I would have explained like that. That things will come in transient with practicality.
Okay, sir. Okay, sir.
Okay.
Okay, thank you, sir.
Okay. So tomorrow, everybody, 7 to 10 non-stop, and day after tomorrow, I will go. Afreen, tell me, Afreen.
सर मुझे डीसी सर्किट्स में डाउट है सर.
बोलो अगर याद है तो मैं बता देता हूँ. आपको प्रॉब्लम डिस्क्राइब करो, मैं बता देता हूँ.
ओके सर एक प्रॉब्लम में पावर डिलीवर्ड बोल तो नेगेटिव लेना ना सर. आप पॉजिटिव
नहीं, सुनो. सी, अगर वो सोर्स है, अगर सोर्स का मतलब क्या है? करंट लीव्स पॉजिटिव टर्मिनल. ठीक है. अगर सोर्स है तो पावर डिलीवर्ड पॉजिटिव है. उसी सोर्स को अगर किसी ने पूछा पावर एब्जॉर्ब्ड, देन नेगेटिव लेना है. सिमिलरली सिंक को देखो. सिंक का मतलब क्या है? करंट एंटर पॉजिटिव टर्मिनल. सिंक का मतलब उधर कोई पूछा तो पावर एब्जॉर्ब्ड करेक्ट है, बिकॉज सिंक को करंट पॉजिटिव टर्मिनल पे एंटर होता है और पावर एब्जॉर्ब्ड करेक्ट है, तो पॉजिटिव लेना है. पावर एब्जॉर्ब्ड पॉजिटिव लेना है. For the same sink, if someone asks what is power delivered, for the same sink, if someone asks what is the power delivered, वो गलत बात है ना, तो नेगेटिव लेना है.
ओके सर. अब ये
बोलो.
से इंटर हो रहा बोलकर यहाँ पर
अगर देखो इधर ये एग्जांपल पे देखो, इधर ये सिंक है या सोर्स है, ये रिप्रेजेंटेशन देखो पहले.
ये सिंक है.
तो किसी ने पूछा कि पावर डिलीवर्ड, वो गलत बात हो गया, तो माइनस लेना है.
ओके, क्वेश्चन से न होके
ये किसी ने पूछा कि इसका पावर अब्सॉर्ब्ड क्या है, वो करेक्ट है ना, क्योंकि सिंक है ना ये.
ओके सर.
पावर अब्सॉर्ब्ड किया तो करेक्ट है, तो प्लस लेना है.
ओके सर टेलीगन्स थ्योरम में ये पावर डिलीवर्ड के 3 प्रॉब्लम्स आप कराए थे ना. में एक प्रॉब्लम में करंट वो सोर्स ही है लेकिन पावर नेगेटिव में नहीं लिए, प्लस में लिए.
क्योंकि उधर पावर डिलीवर्ड इज पावर अब्सॉर्ब्ड, ऐसा दोनों अलग अलग स्टेटमेंट दे दिया मैंने। टेलीगन में ऐसा नहीं पूछा कि टोटल पावर अब्सॉर्ब्ड, ऐसा नहीं पूछा। क्या पूछा? टोटल पावर डिलीवर्ड करके खाली सोर्सेस को पॉजिटिव लिया, टोटल पावर अब्सॉर्ब्ड करके सिंक्स को भी पॉजिटिव लिया।
ओके, मतलब
समझ गए ना?
पावर डिलीवर्ड इक्वल्स टू पावर अब्सॉर्ब्ड होना बोल।
वो पावर डिलीवर्ड करके सोर्सेस को प्लस लिया और पावर अब्सॉर्ब्ड लेके सिंक को प्लस लिया।
ओके सर,
समझ गया ना?
हाँ जी सर, थैंक यू सर।
Right. Okay, right. So everybody tomorrow 7 o'clock.